Your next presenter is Taylor Ricketts. Taylor Ricketts is Gund Professor and Director of the Gund Institute for Environment at the University of Vermont. Taylor's research centers on the overarching question: how do we meet the needs of people and nature in an increasingly crowded, changing world? His recent work has focused on the economic and health benefits provided to people by forests, wetlands, reefs, and other natural areas. He is co-founder of the Natural Capital Project, a partnership among universities and NGOs to map and value these natural benefits. Taylor has also served as an author and editor for 2 UN-sponsored efforts to assess global ecosystems and their contributions to human well-being. Taylor is an elected fellow of both the American Association for Advancement of Science and the Ecological Society of America. Thomson Reuters has named him one of the world's most cited and influential scientists. And here he is, Taylor Ricketts.
Okay, hi everybody. My name's Taylor Ricketts. I direct the Gund Institute at the University of Vermont, and I'm really delighted to be part of this evening session at an online virtual ACES. Thanks everyone for participating. I'm really looking forward to doing that myself. I'm going to be talking about sort of the natural capital accounting and ecosystem service valuation of crop pollination. Specifically, how do we target and how do we value pollinator restoration in working landscapes? So I think this crowd doesn't need a lot of time talking about how much crop pollination is worth and how valuable it is. Suffice to say that about 2/3 of crops benefit from animal pollination, mostly from bees, and that's easily worth hundreds of billions of dollars per year, not to mention providing us with some of the most fun foods to eat that I know about, at least. Also, it's just want to be clear up front that we're talking about, in my view, 2 kinds of bees. One are domesticated honeybees. That's the critter on the left there that we manage actively in boxed hives and move around, versus the 4,000 other species of bees in the US alone that also are good crop pollinators, including this bumblebee on blueberry there, and have enormous diversity, as is shown by this slide, with the world's largest and the world's smallest bee in one frame. So it's not just about honeybees. In fact, my area is mostly focusing on how do we conserve and obtain the benefits from these thousands and thousands of other species of wild native bees that we cohabit our landscapes with. So to me, there are some key issues and research questions that we need to really focus on in order to be able to manage those bees for the benefits they provide us. There are things like, where would pollinator restoration do the most good? If we have limited money, where do we go? Who benefits from restoration? Are we sure we're benefiting who we think we're benefiting? And therefore, who should pay? Knowing who benefits will really let us figure out what the best policies are. And how do we get multiple benefits from scarce land? There's a lot of demand for agricultural land, both in the US and worldwide, and we want to make sure we're conserving pollinators in a way that doesn't compete unduly for other uses that are legitimate and important. So those are the things that sort of drive the work we do and what I want to talk about today. The first 2 examples I want to show of 3 depend on a really simple model of crop pollination, which I will not go into in detail at all, but I want to give you just the intuition about it because it helps explain what we're finding about the questions I just listed. So imagine an agricultural landscape with some natural habitats in green and farms in a farm in yellow here. And for a long time now, more than 12 years, we've been developing a simple model that predicts the patterns of pollination services across this landscape. And we start by measuring the quality of the native habitats for nesting sources and floral resources for bees. And then we estimate how abundant bees are in each habitat for those reasons. And then we essentially let them fly around the landscape all over the place, including to this yellow patch. And we estimate the visitation, that's the V there, of how many bees are arriving on a given farm. We can also even take that visitation with some yield curves and predict the yield due to those additional pollinators to that private farm. That's Y sub P. Okay, so that's it. We estimate where bees are, how abundant they are, we let them fly around, and then we total up how much they're visiting on each farm. So we can tell you more about that model later, but I'll move on for now. One interesting place we've applied this is nationally to ask where to restore habitat. So during the Obama administration, there was a White House release, a memorandum about creating a federal strategy to promote the health of honeybees and other pollinators across the US. And one of the mandates was to restore 7 million new acres of land for pollinators. And the question is, where should we do that? So we use this model to try to answer that question. And kind of skipping through everything, we produce this, which is a map of wild pollinator abundance across the US. Dark blue is where wild pollinators remain abundant. Yellow is where their abundance has been diminished and is low currently. Okay, so if you look at this map, it's kind of a map of agricultural intensification, really, but it shows us where our bees likely are. And it was an enormous effort with a lot of people that I'll skip over. But so we have this map of pollinator abundance. And what we wanted to ask was, how does that supply of pollinators, we can think about that as the supply measure of pollination, how does that relate to demand? And that is where there are crops that require a lot of pollination and a lot of those crops. So we use this sort of color grid to color the map based on the abundance for bees on that bottom axis and the dependency weighted crop area, how much and how dependent is agriculture in different parts of the country. And we're going to zero in on those pink cells with a red outline. That is where there's not a lot of bee abundance, but there's a lot of demand. And we think those are places where there's potential mismatches and risk of insufficient pollination. So here, just again, skipping to the answer, is what we find. The whole country can be reduced to a much more manageable problem of 100 or so counties where we should be worried on a first order approximation about whether there are enough wild pollinators to meet the demand of pollinator dependent crops in those counties. So you can take a look and see where you live, see where you're in one of those counties, and we have a nice interactive map on the web that you can dig in deeper. So the reason these counties are lit up on this map are different. We grow different crops that require pollinators in different places, but they all share the idea that there may be insufficient wild pollination to meet that demand. So these are places, I think, where we should look first for whether rental rates for honeybees to replace this wild ecosystem service are getting expensive, whether crop yields are getting unreliable or lower. These are sort of the places we'd expect trouble first. Okay, so that's a sort of a national application of how can we target restoration efforts, especially when there was this federal, and still is, this federal effort to do so. Okay, another example, I want to zoom into a local example too, which I think might be fodder for discussion after we're all done. And that's asking who exactly benefits from restored pollinators. We all know about pollinator strips and so forth, but who is getting the economic benefits of those? And so we're back to this same model that I showed you before, but we're adding one thing. We're going to have this farmer in yellow restore the edge of their land in blue there. That creates new habitat, so new abundance, and it brings more bees to their farm. It also brings more bees to the neighbor's farm because bees don't respect property lines. And that C is the cost. The cost is borne by the first farm, that original darker yellow, right? So we have benefits to multiple people, but costs only to the person who did the restoration. And that sets up an interesting question about who's getting most of the benefits and do they outweigh those costs? So we tried this out in Yolo County, California, where we have great data on everything we need, who owns what farm, what they grow, and so forth. And cutting right to the chase, we can show that it's different all across the landscape. So the areas in black are where the private benefits, the benefits of pollination to the farmer who did the restoration, him or herself, outweigh the costs. It seems like it's an economically good decision in the black colored farms. In the gray ones, it's an overall good idea, but it doesn't outweigh the cost for the private farmer. So other people benefit enough to make it a good idea, but privately for the farmer who acted, not very much. And then the red ones are where it simply doesn't make sense. Even if we add up everybody's benefit, it doesn't outweigh that farmer's costs. Okay, so right away, again, we can zero in on where restoration would have benefits for whom. It's interesting to see what these farms are, who they are. So that middle row that's in gray are those that have private incentives, the ones that are black on the map. And you can see that they tend to be bigger than other farms. They tend to depend more on bees. The things they grow are more pollinator dependent, and those things are valuable per acre. And that all makes sense. Big farms with valuable pollinator dependent crops are farms that can probably capture a lot of the benefit in themselves. If we had all those farms restore habitat, they'd add $500,000 in private value just within Yolo County itself. But this is the crucial part. They'd also benefit others. $1.2 million in added external value to people who didn't pay for the restoration in the first place. So they're creating private goods for themselves and public goods for their neighbors. If we take a quick policy lens on this, just very, very simply, we can see that those black farms, maybe a payment's not needed. The private benefits are enough to offset their costs. Maybe they need just information and help. The gray areas are where something like a payment for ecosystem service could make sense because the public benefits more than the private landowner does. And then we can really rethink whether it's worth restoring at all in those red areas. So the big point here is that the best strategy varies within a landscape, and we can target funds to best effect if we're careful about that. I just want to say one quick final thing before wrapping up about an interesting idea we're pursuing right now, which is restoring pollinator habitat under solar arrays. This is an idea that's gaining momentum. I think Minnesota's been quite a leader in this, and Vermont is following along. It's a really interesting way to try to restore pollinators in these landscapes in a way that does double service and provides some other benefit as well. So we're studying just how well they do conserve pollinators, and also whether there's a performance change for the solar panels themselves. Okay, so the take-homes from my quick talk here are that we can use these kind of techniques to set national priorities for pollinator management and restoration, that public versus private benefits differ among farms, and knowing that can help us guide policy, and that there are lots of clever, innovative ideas for how to restore pollinators in agricultural landscapes without pushing out other important land uses. So with that, I'll say thanks to these people who supported and collaborated with us, and thanks to you for listening. Looking forward to the discussion.